So I've been at Argonne for a while talking about I/O and working on I/O, and I'm happy to share what I and my colleagues have learned over the years. A lot of people come to us only when they have a problem. Usually it's a bad first meeting. Yeah, so hopefully we have a nice breakfast. It's kind of hang out here in this place. It'll be a little more positive introduction to I/O problems that you might run into. We've done this work, this kind of presentation and this work with a bunch of other people. Even though Rob and I are going to be talking today, a lot of this material came from our colleagues over at NERSC and back at Argonne and so Brent and Katie and Rajiv and Bill and Rusty have all contributed various materials to this, and so some of these faces you've already seen this week. They show up all over the place. So right, this is the training program on extreme scale computing. It is not the training program on how to write I/O real fast, right? The point of all these machines and all these applications is to model something in the world, right? We can't do desktop experiments of a supernova. We can't go back in time and observe the Big Bang, but we can develop models and computational software that runs on these machines. The machines are getting more and more complicated. The models are getting more and more complicated. But this is sort of the trajectory of technology. And for example, the cosmology application you may have talked about, and we'll talk about a little bit today, started off modeling 300 particles. And so their I/O problem was, how do I manage 300 particles? That's not really a big deal. You just maybe even write it in hard-coded. But now the data sets are much larger, much more difficult to manage, and so we need a way to deal with that. So we're going to spend a little bit of time talking about sort of the I/O systems, what's available to us, the technologies that we have available, a little bit about how to think about I/O and what's going on. What's going on behind the scenes. And at one point in here, we're going to be talking about some code examples, a game of life example. And if you want to follow along, that URL has so the code all bundled up. Also on the website, I just 5 minutes ago gave a PDF of this presentation. So in a few minutes, it'll be online if you want to follow along that way. So there are going to be 5 of us today. Rob and I are going to talk in the morning, and then some colleagues will talk to you after lunch. But so just for a little bit of introduction, I've been working at Argonne as a software developer for 12 years. I've been working on file systems, I/O libraries. I work with applications a lot to make sure that they get sort of the experiences and technologies that they need. Rob is my boss. We've been working together that whole time here, and he started off doing parallel file systems, and now he's working on designing storage systems and advising the design and deployment of those things for machines like at Argonne and other places. And he runs the SciDAC SDAV, or co-runs the SciDAC SDAV project. After lunch, you'll get to hear from Quincy. There are probably 3 people who know more about parallel I/O than me, and Rob is one of them and Quincy's the other. So I think you're going to be in good hands there. Quincy works on the HDF5 project, another I/O library for managing these systems. And recently wrapped up an exascale fast-forward storage project, which created some pretty fun products. Avery Cheng, who used to share an office with me back at Argonne when he was a student, will be talking about sort of the Facebook way of doing I/O. We have, today we sort of have 2 ways of looking at storage problems. We have the Department of Energy or leadership scale system, big checkpoints, big restarts. And then we have, I don't know what the right term for it is, I call it the Silicon Valley I/O model, and Avery's going to talk a little bit about sort of the graph processing that goes on in a situation like Facebook would do. And Rashana will talk about Globus and their way that they manage data, and whereas some of the libraries and technologies we'll talk about this morning are about how applications deal with data in place. The Globus product that she's going to talk about is how do you ship and deploy these terabytes of data to your colleagues all over the world. With the, we're talking about I/O as an I/O system, and this is going to be not just the hardware, but all the software and the applications using that software. We have ever-growing storage performance requirements. The amount of storage is secondary. You almost get that for free, because in order to get enough performance out of these disks, you have to have thousands of them. So we manage that with several layers of abstraction layers. A hard disk, the disk itself, they're enclosed in drive enclosures, and those are managed by RAID devices and storage servers, and so this all propagates up down through to the application finally. Now the application is going to be doing a couple different things. Either often checkpoint I/O. We used to think for a while that was the dominant way of doing I/O. We're just going to be every couple hours we'll write a checkpoint, so that if we are interrupted or we lose power interruption or whatever happens, we can restart our work. But it turns out that there's a productive part of this too, not just defensive. You're either going to be generating some kind of consumption, generate an image or a plot that'll be consumed by a subsequent step in your workflow, or you'll be reading in sort of input decks or data sets to feed your application. And so that style of I/O is going to dictate what's important, but the tools that we develop can sort of fit both of those styles. Now, not only are the amounts of data large, but the way that data is structured is increasing in complexity as well. So no longer, as I mentioned before, is enough to just sort of have a list of data. That data has semantics with it. And sometimes those semantics isn't just one set of semantics, it's several different things. So for example, consider these figures which are taken from a simulation that's modeling a nuclear fuel assembly. You have the whole reactor. You want to model the current, the convection currents as the coolant cycles through the fuel assembly. You want to model the entire fuel assembly too. You want to make sure that you have the neutrino effects and everything else that's going on there. And you want to model the fuel pellets themselves. And so this is, the size of a building, and this is the size of a pencil eraser or something like that. So the I/O software stack is managing not just how much data we have, but the fact that the data has many different characteristics. This graph is getting a little bit old, so we're going to work on updating it. But the point is that the application groups that are coming to these machines, applying through Insight and other venues, are working on quite a large amount of data, hundreds of terabytes. This is probably on the order of petabytes now, after these couple of years have passed. Excuse me. So even though we think about top 500 and how fast is your computer speed, how fast are the interconnects, these applications are also moving tremendous amounts of data, and being able to meet those needs means they can do more science, right? They're not thinking about how fast can I manipulate 100 terabytes. They're thinking how fast can I model energy storage, or how fast can I simulate the climate, how fast can I model laser plasma interactions. These are what the scientists want to do. So the bottom line here for all of our design decisions is getting back to science as fast as possible. So things that get in the way of science, not just writing out checkpoints, but reading in simulation data, reading in the input decks, because the scientific applications are, again, not just monolithic applications. They're typically existing as part of a workflow, and so these writes are both defensive and productive. These reads are generally the pipeline, the workflow pipeline, as they pass from one step to the other, or as they feed it off to the analysis and visualization group. You'll see quite a few variations of this software stack diagram. We'll add more to this as we go through. But a good way to looking at the way the I/O works is in the bottom here. The I/O hardware is basically a bit bucket holding data with a very simple view of how things are supposed to be. And as we work up the stack, we apply a storage model, we apply transformations on that data, we add the application data model, and things get more sophisticated as we go from I/O hardware up to the actual way that things are managed on the compute nodes. And so each one of these steps allows us to do something clever and allows us to help make I/O go faster, but it's also a step where things can go wrong if certain assumptions are made that are incorrect, or if a workload isn't quite what the software layers expect. So there's 1,000 different ways you can tune this, and knowing where to begin can be a little tricky. And again, that's what tutorials like this are for. In the old days, a few years ago, HPC systems were pretty simple. You'd have your plain file system. It would be a bunch of POSIX files. You would figure out some local proprietary way of doing that. Maybe you make your own header and indexing, and you have sort of your application would write this kind of file. And it would all go over a pretty simple Ethernet switch. Linux clusters would be the kind of thing that you would have now, or kind of a dime a dozen. This was pretty easy to understand. We would set up simple servers and deliver this pretty well. But now, Mira, Oak Ridge machines, Titan and Jaguar, the NERSC machines add more to that. The scale is increased such that a simple model of how things are working isn't quite adequate. We need to add a little bit more to that. Instead of a simple switch, we have say Mira, right? We'll talk about this in more detail in a few slides. But there's a way for all the compute nodes to talk to each other that's probably a little bit different from the way that the storage talks to each other. There are going to be I/O forwarding nodes that help manage with scalability and resiliency there. So, with more complexity, there are some more opportunities, but more pitfalls too. The notion you should keep in your mind as we go through today, both when Rob and I are talking and after lunch, is the idea that there's not just data on disk that we need to worry about. It's the way that data, it's the meaning behind that data, right? And the fun thing about that is the more semantics, the more meaning you can give to the data, the more opportunity a guy like me or the libraries I work on have to make things run more smoothly, run more efficiently. Sometimes we'll run into cases where computer scientists in an effort to make things happen, right? Their goal is to do science, will try to invent these things on their own for their application, and they do okay, but again, they're computational scientists and will often make some of the similar mistakes that we've already made 5, 10 years ago. So the lesson here should be there are a lot of complexities. You don't have to solve it on your own. There are a lot of resources out there to help make things easier, even though they may seem to make things more complicated. Right, more abstraction layers, more libraries involved, but that's the opportunity to sort of make things easier for the storage system. So I'm going to flip it over to Rob now. He's going to talk a little bit about HPC systems and sort of the the underlying layer, and we'll work our way up the stack through the day.
Thanks, Rob. So I want to step back for just a second and reiterate something that Rob mentioned. As we sort of walk through the day, I want you to try to keep in mind these two views that are articulated on this slide on the left and on the right. And on the left is sort of a way of thinking about how an application might have internal data structures, right, that are relevant to the simulation or relevant to the experiment at hand. And in some sense, from the top to the bottom on the left-hand side, we're thinking about the ways that the data is perhaps logically transformed so that we can then capture important characteristics of that data persistently so that we can come back to that data later. And then how we then map those components of those abstractions down into a storage model. And in our case, we'll focus mostly on files and directories, but that could be an SQL database. It could be a graph database. It could be some NoSQL or key-val store. But the notion being that we start from the perspective of the science problem we're trying to solve, and then through a set of transformations, map those things down into whatever the organizational tools are that we have at hand. And in our case, it'll primarily be parallel file systems we'll talk about for the first half of the day. On the right-hand side, is in some sense, an entirely different way to think about the problem, which is that, well, that data that we're operating on in our application is sitting in memory somewhere in the memory hierarchy. And when we go to store it, it's going to have to move from, banks of DRAM through buses, over network interfaces, through controller cards on different servers, and ultimately out to disk drives, right? Or maybe to NVRAM if you have enough. And so on the one hand, we'll be thinking about what are the sort of the logical transformations that we're making so that we can understand the data that we've saved and retrieve it. And on the other hand, we'll be thinking about how do we move this data most efficiently through what is a pretty complex, highly parallel data path. And so with that in mind, I want to talk about how HPC systems work. And we're going to start at the bottom with file systems. And so, with that sort of leftmost, view in mind, HPC I/O systems provide us what we think of as a file system view. It's the same view that you're accustomed to seeing on your laptops of files and directories, and maybe you know that attributes get stored on files, or maybe you haven't noticed that or had to deal with that. If you copy files back and forth between Mac volumes and other places, you'll find that things get lost sometimes, and that's why. In addition to that sort of notional file system view, there's also a model for sharing that says that if different processes are interacting with the file at the same time, there are rules for how that plays out. And in HPC systems, that often includes the login nodes, right? So that you've got a way to get data on and off the system. So what we're going to talk about is sort of how data is stored and organized. Ultimately, we'll be talking about what tools we have to help applications organize data. And there are tools beyond this file model. And how we manage concurrent access and things that we do to try to make things go faster. This diagram on the right is just to remind us that we have folders or directories, that we tend to have files, and that when we think about files, we can think about them being broken up into chunks that are just contiguous regions of the file that may or may not, that are stored in some way or another, whether that's on individual disks or something else. Now, in an HPC system, we build HPC systems with what we call a parallel file system. Parallel file system is a distributed system. We interact with distributed systems all the time these days. That wasn't true as much when I was coming in grad school, but nowadays I think people are accustomed to the notion of distributed systems. With a parallel file system, the distributed system that is the parallel file system is managing a bunch of devices, thousands, tens of thousands of drives, hundreds, maybe thousands, but probably hundreds of servers, and a very large number of network links, and then presenting that with that file system abstraction, so allowing you to look at all of those resources as if they were one collection of directories and files. And one of the properties that we expect out of a parallel file system is that, at least under the right conditions, different clients in our HPC system ought to be able to interact in parallel, concurrently with that file system resource without, without being bottlenecked by one another. And that we'll talk about when you should expect that and when you shouldn't over the day. So to dive down one more level of detail, if we look at a diagram where we think of our clients at the top and our servers at the bottom, a parallel file system specifically is some software that runs on clients, usually in kernel space, and some software that runs on servers. And those things communicate with one another in sort of a remote procedure call-like mechanism, but they're communicating over a network in the same way that your laptop interacts with an HTTP server, for example. And so one thing to keep in mind is that unlike on your laptop when you say, I want to look at the listing of files in a directory, and that's all local, right? You're just interacting with the operating system. Here, when you ask the file system to do something, that goes into the operating system. The operating system bundles up the request and ships it over a network to another server who receives that and performs whatever the operations are and then responds with the data. And so one thing that we have to keep in mind when we're thinking about performance in these contexts of HPC I/O systems is that latency is going to matter. And in fact, on current day systems, the picture is a little bit more complicated, and Rob alluded to this. And in fact, on most systems today, there's a set of intermediate nodes that sit between some very large number of compute nodes and some number of storage servers and disk arrays that are sort of intermediates. And on the Blue Gene system, those are I/O forwarding nodes. They might be the Lustre gateway nodes on a Cray system. They're there, and it's another layer of indirection between the client and the storage system that has some advantages, but also, again, imposes some additional overhead in the system. And so when I bring that up, part of the reason I bring that up is that one of the early things to understand and an expectation to sort of build when interacting with an HPC I/O system is that there's going to be this latency. And so anytime you interact with the storage system, you want to do as much as you can with any one interaction. So if you have, let's say, a megabyte of data that you'd like to store, ideally you would tell the storage system, hey, here's my 1 megabyte, please store it, not give it to it in small bits and pieces. And this graph is from our prior Blue Gene system at Argonne, but really sort of shows this trend quite clearly. So here we're looking at 4 kilobyte request sizes, and here we're looking at 4 megabyte request sizes. And you can see that there's a very sharp difference in both reads and writes between those 3 orders of magnitude of change. And this is not a trend that's going to change anytime soon in storage systems. And in fact, groups have done studies where they've said, okay, well, what happens if we replace all the disk drives with solid state drives? But we keep the file system the same, and et cetera. And you may get a factor of 2 performance difference, but the trend is still there, and it's because you have all this latency, and also because the parallel file systems, frankly, weren't designed with the expectation that they were going to have these very low latency devices under the covers. And so this is one factor that we'll be coming back to over and over again, and we're going to be handing you some techniques to help you organize interactions with the storage system so that there are fewer and larger interactions. So to continue our sort of dive down on parallel file systems, this diagram shows here sort of a logical view of a file broken up into chunks, okay? And here is sort of a high-level representation of how the storage system thinks about a file. And this is true for a Panasys file system or a Lustre or a PVFS. GPFS operates a little bit differently. We could talk about that over lunch, but conceptually you can think of it this way as well. Logically, a file has a name and then some parameters associated with it that are containers that data is going to go into, and basically a mapping of regions in the file to those containers. And so in this case, there were 4 containers associated with this checkpoint, and there's a round-robin mapping so that the first region of data in the file goes to the first container, the second region of data goes to the second container, and so on. And so what file system clients are doing is retrieving this data, and then when you go to interact with the file saying, okay, well, this user's trying to access this 5th extent out here, and so I need to calculate where that is. Okay, that's over here in this particular second container. Now I'm going to go and interact with that server to get that data or to put data into that container. And so there'll be this, in some cases, multiple steps to go and retrieve that metadata, often on the first interaction with the file. And then after that, clients tend to go directly to the file servers that they're interacting with, the storage servers they're interacting with. Another thing you can sort of read from this is that, well, if a particular application process wants, say, the first 4 blocks, then they're going to need to interact with 4 servers. On the other hand, if they were to read every 4th block, they would interact with 1 server. Now, that's tricky to actually decode as a user, but there are libraries that can help us play games where we can say, okay, well, we know We have way too many clients to interact with to have each one interact with every server. And so we'll do some organizational tricks to cut down the number of clients that interact with a particular server at one time. And we'll see that later today. So if we step up a couple of layers and we think about this logical view from the top and say, okay, well, what do applications maybe think, how do maybe applications want to think about data storage? And ignore that file system view for a second. Many applications operate on dense multidimensional arrays, right? And even in applications that operate on sparse arrays or that operate on collections of particles, for example, in many cases it's fairly simple to translate those types of data structures into dense multidimensional arrays. And if you look at the kind of support that the HPC storage community has provided for application teams to use, whether that be an ADIOS or an HDF5 or a parallel net CDF, dense multidimensional arrays are the things that the HPC storage infrastructure is best at supporting. And so what you'll see for most application teams today, if they're using these types of things, they're making some translation from the data structures that they have, which may be dense multidimensional arrays, which is great. But if not, they're transforming that into a dense multidimensional array organization that they then store in files. And so we'll talk about 2 or 3 examples of how to do that today. And if you have a particular example that you'd like to talk about, catch us at the break or catch us at lunch, and we'll dive into what might be unique about the way you'd like to store data. But this particular example is how NetCDF and Parallel NetCDF manage this. And so on the left, we see a couple of multidimensional arrays. And on the right, this is the NetCDF file format where there's metadata stored at the beginning of the file in a header that describes what's going to go in the file. And then these arrays are then laid out in contiguous regions subsequently, right? And so this then becomes a portable file that you can move around between different file systems, between different architectures, and still access the data in a coherent way. And you don't have to worry about the fact that maybe integers are a different size or Indian is different on this machine, things like that. It becomes a portable format. So there's a lot of value in this sort of thing. But to the first order, the most important thing is that the application no longer has to think about all that, what bytes are located where, and instead can think about arrays and dimensions and files and variable types. So to sort of pull all this together and sort of recap, we have an application at the top, and we have some I/O hardware at the bottom. And we have a set of software layers in between that are going to help us in moving data between those two. That last thing I talked about, we're going to categorize as sort of data model support, and that's going to help us by providing some abstractions that make it easier to move from the data model and organization and application memory into something that we can store. Rob is going to talk about a set of transformations that often get applied that ultimately get us down into bytes that are distributed across a very large number of servers and drives managed by a parallel file system. And we'll talk about ways you can learn more about how the file system's operating, et cetera, as the day goes on.